Hi everybody, in this video or a section of videos, we're going to look at rational functions and their graphs. So rational functions have the word ratio in it, and ratio is sort of like a fraction. A fraction is one example of a ratio when we have one thing compared to another. So here you have a function that's a fraction, and the numerator and denominator are polynomials, and that's what a rational function is. So it's the quotient of two polynomial functions. So it looks like this, p of x over q of x. And of course, you need to make sure that q of x is not 0. So for your domain here, it's going to be all real numbers, except any values that make the denominator 0, because remember, that would make it undefined. So to find the domain of each rational function, it's pretty straightforward. You're going to always check the denominator. So what you're going to do is set each denominator equal to 0, and then we're going to exclude that value. So you need to make sure your denominator is not 0 here. So for the first case, I have x minus 3. I add it to both sides, and I have that x equals 3. Now remember, this is a bad value. This would make the denominator 0. So our domain here is going to be all values such that x is not 3. And if we write that in interval notation, it'd be negative infinity to 3. Union 3 to infinity. So we skip over that value of 3. It's worth noting here that if you were to factor the numerator, you would get x plus 3, x minus 3. So you may notice that that x minus 3 factor does cancel, but you still have to do the domain first. So even if you are simplifying your expressions and you're starting with a rational expression that looks like this, for instance, you still want to do your domain before you continue simplifying. For the next one, we're looking at x squared minus 9. And again, I need to make sure that x squared minus 9 is not equal to 0. So I'm going to find the bad values here. And you can solve a couple different ways. Now, one way you could solve is you can remember that this does factor as x plus 3, x minus 3. So then you would have each of those factors set equal to 0 here. And here you would subtract 3. Here you would add 3. And you get those two values that you should exclude. For this problem, there's actually another way you could do it too. You could add the 9 to both sides first to start, and then you could take that square root of both sides. Remember that we do take the positive and negative square root, so you'd end up with still positive and negative 3 as your values. So in this case, you have two values that you're excluding from the domain. So here we're excluding two values. So we're jumping over negative 3 and jumping over positive 3. And remember, when you're writing an interval notation, to always go from left to right or least to greatest. All right, so we have one more example here. And for this one, again, we're looking for where does the denominator equal 0 here. And I want you to notice something. If you think about x squared values are always going to be either 0 or positive, right? They're never going to be negative. When you square something, you cancel that negative out. So this value here is never going to actually end up being equal to 0. It's actually always going to be positive. And what happens when you try to solve, you would bring that 9 to the other side, and you'd actually end up with an imaginary number. So you'd have plus or minus 3i as your result. And for domain, we don't really care about imaginary numbers as part of the answer. It doesn't make sense here. So this has no issues to worry about. This denominator here is always going to be positive. It's never going to be 0 because you have a 9 here. And then your x squared has to be at least 0 as well. So the smallest it's going to be is 9. So this has no issues. So it does work out where sometimes you do have rationals that end up not having a domain restriction, and that's because the denominator will never be 0. And this is just one example here. So now I want to look at actually graphing rationals. So this is the basic rational function. It's called the reciprocal function, and it is 1 over x. So what I want to do is just kind of plug in some different values, see what happens, and then show you what the general shape looks like. So do notice here that x cannot be 0, right? That would make my denominator 0. So x is not in your domain. We do have to exclude that from the domain. But otherwise, I can pick any values that I want. So I do like to pick some positives, some negatives. Because x cannot be 0, I do want to pick some values that are close to 0 as well. So I'm actually going to pick some fraction values here too. So let's start with our positives first. So I think I would like to look at maybe 1/4, 1/2, kind of heading towards 0 there, right? 1/4, 1/2 would be the next bigger one. Maybe we'll look at 3/4 at 1, 2, and 3, and then we can look at negative values too. So here, when I plug in my whole numbers, I think it's pretty straightforward. We're just doing 1 over that whole number. So you'd have 1 over 1, which is just 1 here, 1 over 2, 1 over 3, etc. Right? If I went and did 10, for instance, 1 over 10. So you're getting these smaller and smaller fractions. When you plug in your fractions, you do want to be a little careful. So you have 1 over 1/4. So that's the same thing as 1 divided by 1/4. And remember that for fractions, division is actually the same as multiplying by the reciprocal. So this is the same thing as multiplying by 4 over 1. We flip that second fraction. And that is just 4 here. Same thing if we did 1/2. So it'd be 1 divided by 1/2, which is 1 times 2 over 1 or 2. And then if we did 1 over 3/4, we 1 times 4/3, which is 4/3. 4/3 is 1 1/3, or about 1.33. So if you're having trouble graphing, you can always plug it into your calculator as well. And I kind of ran out of room here, so I'll do it at the bottom, but you could go smaller fractions as well. If I did 1 over 10 instead, you'd have 1 times 10 over 1, which is 10. So what I hope that you're noticing here is that as your integers get bigger that you plug in on the positive side, your fraction actually result gets smaller, right? It's getting kind of closer and closer to 0. And then as your fractions get smaller, right, they're actually getting bigger for the y output. So let's graph some of these points. All right, let's see. I have 1, 1, which is right here. That's a nice clean one to graph. Now 2, 1/2, I'm just going to estimate. 3, 1/3, 10, 1/10. Looking at my fraction side, 3/4, I'm a little bit over 1. So maybe I'm like right here. And then at 1/2, I'm at 2. At 1/4, I'm at 4. 1/10, I'm at 10. So what's happening here, and bear with my drawing, but you're getting a graph that kind of looks like this. So you have this like branching graph. And as you go closer or bigger x values here, you get closer and closer to 0. And as you get smaller x values, you become bigger and bigger and bigger on that y-axis. So you're kind of shooting up to infinity that way and then heading towards 0 in the other direction. Now, if you were to plug in the negative values, you'd actually get the same result, right? So if I make these all negative, right, negative 1/4 is just going to end up changing my answer to -4. Negative 1/2 is going to change this to -2. So by plugging in the negatives, we're actually just, basically still looking at the same type of problem. It's just that all my values become negative here instead, right? So on the other side, you'd have something very similar. So at -1, -1. And then here, as I get closer to that axis, our values are getting bigger. And then as I get further left, our values are getting, again, closer to that axis. So it looks like this. And that's the graph of f of x equals 1 over x. So remember, we said that for the domain, x cannot be 0, right? So notice how we're not touching 0 on the x, that line x equals 0. We're having this like split here. So this branching off in either direction. So you have your positive side, you have your negative side, but actually we're never going to touch 0. It's going to get closer and closer and closer but you'll never actually have a point on x is 0 because that would be undefined. And you do notice a lot of times, not with every single one, but with a lot of rationals, you do have this sort of splitting idea. You may have one split, you may have multiple splits. So we're going to look at these different splits throughout the next couple of videos because they have different names as well. So we see that things that kind of split vertically like this are called vertical asymptotes. And then horizontally here, you actually have a horizontal asymptote. So we'll talk more about those definitions, but it's pretty common in most rationals to get at least one split, if not multiple splits in the graph. All right, one other thing I want to talk about is notation here. So you're going to see this notation starting to be used, and we use it a lot more in upper level math classes. This arrow sort of means approaches or goes to. So we're saying here that as x approaches or x goes to this value. Now, when you have a little plus sign there, it means from the right. And when you have a negative sign, it means from the left. This would mean what's happening as x goes to infinity. And this would mean what's happening as x goes to negative infinity. So if we go back to our graph on the other page here, so I don't know if I'll be able to keep them both on the screen. We'll try. But let's kind of look at some details here, but let's see what's going on, right? And we're going to use this graph as our focus. So let's do the bottom two first. I think that's our easiest to see. So as x goes to infinity, right? So as x gets bigger and bigger and bigger, right? What's happening here? Well, the graph is flattening out, but it's getting closer and closer to y equals 0, right? If you think about plugging in that 10 value, we had 1/10. So you're getting closer to 0, but you're not actually going to touch it. So as x goes to infinity, f of x is going towards 0. Now remember, f of x is the same thing as y. So we're looking at the y value here. Now, as x goes towards negative infinity, meaning we're going in this direction, x is getting smaller and smaller and smaller. Well, what's happening with the y values? Again, those y values are approaching 0, right? They're still negative, but they're getting closer and closer and closer to 0. So again, f of x goes towards 0 here. Let's do a couple other examples using some numbers here. So what happens as x goes to 0 from the right? So remember that plus sign means to look from the right. So here we're looking as x goes to 0, here's 0, and we're coming in from the right direction, meaning like looking in this way. So as x goes to 0 here, what's happening is our y values are getting bigger and bigger and bigger and bigger and bigger. So those y values are approaching infinity. So f of x goes to infinity. Now what happens as x comes to 0 from the left? So again, we're moving in from the left direction, so we're coming in this way. And as we get closer and closer and closer to 0, what's happening with those values? Well, we're getting lower and lower and lower and lower and lower. So we're going to keep going down and down and down and down and down. So your y values are going towards negative infinity. So this is some new notation that we're going to bring in here. Just kind of thinking about, well, what trends or patterns are we seeing, right? Is there a specific thing that's happening? So as x goes to infinity, like the values aren't changing. They're not going up and down and back and forth. They're all heading towards 0. It's consistent. There's a pattern there. And same thing on the other side. As we go towards negative infinity, again, that graph is not going up or down or bouncing all around. It's clearly going in the same pattern. It's going towards 0. And then similar ideas here, right? So we have this very clear pattern that the same thing is kind of happening as we get closer and closer and closer to 0. As you get into higher mathematics, we a lot of times call this notation, we use the words limits as well. So if you hear that terminology, then that is fine. Something to watch out for.